Hello and welcome to the BS Academy. We hope that your preparation is going well. So let's start the next video. Before that, if you are new to your academy, then please subscribe for the coming videos and the links for the short notes which are in description box. This is the second chart of the heat transfer in which we will start the remaining portion of the conduction. And in the first chart we have included the basics as well as the portion of conduction in which we have completed the one-dimensional steady-state heat conduction equation as well as the thermal resistance and the critical thickness of insulation. You can check out that short note. As you can see here, the first concept in the second chart is fins. Fins are extended surface and heat is transferred by the convection. It is used to increase the convective heat transfer and reduce the temperature of one side. The equation will be Q is equal to HA into Ts minus T infinite. Then after first one, governing differential equation for fin. So del square theta upon del x square minus m square theta is equal to 0, which is the equation for the fin. Then after theta is equal to C1 into cos h into mx plus C2 into sin h into mx. Then for infinite long fins, theta is equal to theta naught into e raised to minus mx. Then m is equal to under root hp by k into area of cross section. Then the second one is for infinite long fins, theta is equal to theta naught into e raised to minus mx. Here theta is equal to t minus t infinite and q is equal to under root h into p into k into cross section area into theta naught. Then here m1 is greater than m2 greater than m3, and for ideal case theta by theta naught is equal to 1 and q is equal to HA into epsilon f into theta naught. Then third one is for insulated fin tip, theta is equal to theta naught into cos hm into L minus x divided by cos h into ml. Then similarly the equation is given for the convection at tip. Here LC is equal to L plus D by 2 for rectangular fin and LC is equal to L plus D by 4 for cylindrical fin. Then after some more equations are there, you can take a screenshot for the efficiency and the emissivity of the fin. Then there is one example which was asked in the GATE examination. The conical fin enhance the heat transfer rate because more area at more temperature difference. Then you have to include the Q loss is because of the air convection as well as the air radiation. Then there is some more notes are there. First one is the critical insulation thickness of steam, then Q will decrease. Then for steam boilers, adding insulation will decrease the Q. You have to remember just one line that by adding the insulation in the boilers, the Q will decrease. Then in the electric wire, first the Q is increased up to the critical radius, then after the Q will decrease. Here two more examples are there. Now the next topic is transient heat conduction. The governing differential equation is del square T plus Q by K is equal to 1 upon alpha into del T upon del T. Here temperature is function of both space and time. So you can say that T is equal to F of XYZ and T. Then one more important topic is there, which is lumped heat analysis. It is an analysis in which the temperature varies only with the time but not with the space. So you can say that T is equal to F of T. Here note that possible causes for lump system is, first one is thermal conductivity is too much higher, then the conduction is resistanceless, and the second one is the object is very small. Then the next topic is the time required by a system to reach particular temperature. Here the equation will be, here the equation is HA T infinite minus T is equal to mCp into dt upon dt. Here the equation is HA into T infinite minus T is equal to MCP into dt upon dt. Then T minus T infinite divided by T naught minus T infinite is equal to e raised to minus HA upon rho CV into T. So you can say that theta by theta naught is equal to e raised to minus Bt. This equation is also very useful. Then T is equal to T2 plus T1 minus T2 into e raised to minus Bt. Body is cools down, and when the body is heats up, in both the cases T3 greater than T2 greater than T1. Then characteristics length for various shape. Here for the slab LC is equal to L by 2. Then for sphere LC is equal to R by 3. For cylinder LC is equal to R by 2, and for cube LC is equal to L by 6. Then after for lumped system BI is equal to HLC by K less than or equal to 0.1. Then theta by theta naught is equal to e raised to minus BI into FO is equal to T minus T infinite by T naught minus T infinite. Then Fourier number F naught is equal to alpha T upon LC square. Then BI is equal to minus HA upon rho CV. This is all about the conduction chapter. Now we will start the next one, which is convection. And if you like this video, please do like and subscribe to our academy. Then here in the convection, first one is the definition. The heat transfer in presence of a fluid motion on a solid surface is given by convective heat transfer, and the equation for that Q is equal to HA delta T. Then classification of convection flows. First one is based on the driving mechanism. First one is forced convection, the second one is free convection. Then after based on the geometry, there are two types. First one is internal flow and the second one is external flow. Here in the internal flow, fluid is surrounded by the solid body that can resist the development of boundary layer. The example is flow through pipe. Then in the external flow, fluid is unbounded by a solid body, so that in the external flow, boundary layer can be developed. Then after boundary layer concept is there, it is a fluid layer over the solid surface in which the gradient exists, and if the viscous force is sufficient, then velocity gradient exists, which is called the velocity boundary layer, and it is also known as the hydrodynamic boundary layer. Then after, if the thermal force is significant, then temperature gradient is exists, and it is known as the thermal boundary layer. Here note that the above boundary layer temperature and velocity of the fluid is same as free stream condition. Then after boundary layer thickness, the equations of that is very useful. Delta is equal to 5 into x divided by Rex. Here delta proportional to PR raised to 1 by 3 into del T. Then delta is proportional to root x, is proportional to 1 upon hx. Here in general you have to remember that Q is proportional to 1 upon del T, 1 upon dt and 1 upon LC. Then this note is most important in the examination because frequently the questions were asked based on the relation between these two, del and del T. So for PR is equal to 1, which is Prandtl number, delta is equal to delta T. Then for PR is less than 1, delta is less than delta T, and for PR greater than 1, delta greater than delta T. So in general you can remember that PR is proportional to delta. Here delta is for hydrodynamic boundary layer thickness and del T is the thermal boundary layer thickness. Then after force convection correlations, first one is the Nusselt number. Here Nu is equal to HLC by K. Then after Reynolds number, R is equal to rho L by mu. Then the third one is Prandtl number. PR is equal to mu Cp by K. Then drag coefficient Fd is equal to Cf into rho square by 2 into A. Here it is the value of average drag coefficient. Then fourth one is Grashof number. Here Ra is equal to Gr into Pr. Then after Reynolds-Colton analog, here St is equal to Nu upon Re into Pr. St is equal to Stanton number and Nu is equal to Nusselt number, R is equal to Reynolds number, Pr is equal to Prandtl number. Here Ra is equal to Gr into Pr, where Ra is equal to Rayling's number. Here Ra is equal to Gr into Pr, in which Ra is equal to Rayleigh number, Gr is equal to Grashof number, and Pr is equal to Prandtl number. Then the local nature of convective correlations. First one is for the laminar flow, or you can say that the flow over a flat plate with the constant wall temperature. Here first one is laminar flow, in which a flow over a flat plate with constant wall temperature. Then local temperature. Then value of local Nu is equal to, then the equation of local Nux is equal to 0.332 into Rex raised to 1 by 2 into Pr raised to 1 by 3. Here H bar is equal to 2 into HL. Then average Nu bar is equal to 0.664 into Re raised to 1 by 2 into Pr raised to 1 by 3. Then for the here in this type the temperature is constant, and in the second type for heat flux is constant. Here the value of Nu is equal to 0.453 into Rex raised to 1 by 2 into Pr raised to 1 by 3, and Nu bar is equal to 0.906 into Re raised to 1 by 2 and Pr raised to 1 by 3. Then similarly for the turbulent flow the equations are given. Constant. Then here one more note is there. HL bar is less than that of HT bar, and H bar at T is equal to constant is less than that of H bar at Q is equal to constant. As well as the third note is there, at T is equal to constant H bar is equal to 2 into HL, and fourth note for Q is equal to constant H bar is equal to 1.25 into H. From these four notes so many times questions were asked, so just you have to remember these notes. Then for the free convection the equations of the horizontal plate and the vertical plate are given there. You can take a screenshot. Then here Nu is equal to Q convection by Q conduction is equal to R conduction by R convection, which is always greater than 1. Then for pipe flow two conditions are there. First one is for T is equal to constant, and in the second one the Q is equal to constant. So you can take a screenshot for that equations also. Then after volumetric expansion coefficient beta is equal to 1 minus -1 upon rho into d rho by dt at P is equal to constant, and Nu is equal to 0.15 into RAL raised to 1 by 3. Then after for free convection, then after this table is also very important for finding the value of LC and L. Here for the free convection for horizontal plate LC is equal to AS by P. Similarly for the force convection LC is equal to L. Then in the horizontal cylinder LC is equal to D and LC is equal to L. Then for horizontal circular plate LC is equal to D by 4 in the free convection, and in the force convection LC is equal to D. Then vertical plate LC is equal to L for both the convections. Then here Nu is equal to 0.15 into Ra raised to 1 by 3 is the equation for the free convection. Here n is equal to 1 by 3 for the turbulent flow and n is equal to 1 by 4 for the laminar flow. Then the third chapter is heat exchangers. Here first one is the definition. It is device in which heat transfer occurs from one fluid to another fluid, mainly used to condense the vapor and to evaporate the liquid, also to recover the heat. First, here the classification of heat exchanger. In that, first one is based on heat exchanging process. In that type also there are two types. First one is the regenerators and the second one is the recuperators. Then based on the relative direction of motion, three types are there: cross flow, parallel flow and the counter flow. Then there is the special case. For that, the equation of Q is equal to UA into theta m. Here for the same heat transfer, the area of parallel flow is greater than that of the area of counter flow. Hence the counter flow heat exchanger is more economical for the same heat transfer. Then after LMTD, which is most important for the gate examination, the full form of LMTD is logarithmic mean temperature difference, and the equation for Q is equal to UA theta m is equal to theta naught minus theta L upon ln theta naught upon theta L. Then NTU is equal to number of transfer unit, and the equation for that NTU is equal to UA by m dot into Cp small, and effectiveness of heat transfer for the parallel flow, epsilon parallel is equal to 1 minus e raised to minus NTU into 1 plus C divided by 1 plus C. Then epsilon counter is equal to 1 minus e raised to minus NTU into 1 minus C divided by 1 minus C into e raised to minus NTU in bracket 1 minus C. Then after, two special cases are there. First one is for gas turbine and recuperator. The equation of epsilon parallel and counter is given there. The equation of epsilon parallel is equal to 1 minus exponential of minus 2 into NTU divided by 2. Then epsilon of counter is equal to 1 minus exponential of minus NTU. Here note that for gas turbine and recuperator C is equal to 1. Then the second case is for boiling and condensation, C is equal to 0 and epsilon is equal to 1 minus exponential raised to minus NTU. And the next topic is the radiation. This is just brief introduction about the radiation. In detail we'll discuss about that in the last chart of heat transfer. Here first one is the definition. Radiation is the energy emitted by matter in the form of electromagnetic waves as a result of changes in the electronic configuration of the atoms and molecules. Then in radiation, the internal energy of the object decreases, and there is one chart for electromagnetic spectrum or wave. Then here note that in the infrared curve, lambda range lie between the thermal radiation and the microwave. Then for the second one, thermal radiation can be reflected, refracted and subjected to scattering and absorption when they pass through the media. Then the final note for this chart of heat transfer, that the properties of emission mainly depends on temperature, nature, wavelength and the frequency of the radiation. So this is all about the second chart of heat transfer, in which we are discuss about the remaining portion of conduction as well as the convection and the heat exchangers. Now in the final chart of the heat transfer, we will discuss about the radiation portion. So please do like and subscribe for the upcoming chart of radiation. And if it is useful, then share to your other friends also. Thank you so much.